Hello everyone, welcome to the first video in the series on CUDA GPU programming. In this video, we'll cover the key architectural differences between CPUs and GPUs, the fundamental design trade-offs, and what this means for how we write parallel code. Let's get started with the CPU. Here, I'm showing a single core CPU. You can see the execution core, the control logic, multi-level cache system, and connection to DRAM. CPUs are designed to handle diverse workloads. These include operating systems, databases, I/O operations, peripherals, and even network applications. This breadth of responsibility shapes the architecture of the CPU. The CPU is designed to minimize latency. That is, when an operation is issued, it should be performed as fast as possible. Therefore, each core is optimized for single-threaded performance and features complex architecture with a deep instruction pipeline, branch prediction, speculative execution, and many more. Additionally, the multi-level cache system helps optimize data movement by keeping frequently used data close to the execution units. For decades, CPU performance has improved mainly by improving the clock speed. However, in the mid-2000s, that trend started to slow down. Power and heat became the limiting factors, and clock speed plateaued. Now, to keep performance scaling, the industry shifted towards multi-core processors. Instead of one faster core, we now have multiple cores working in parallel. Here I'm showing a multi-core CPU with about 4 cores. Modern CPUs typically have anywhere from 8 to 128 cores depending on the segment. Each core retains the same sophisticated single-core architecture with branch prediction, out-of-order execution, and so much more. For workloads with moderate parallelism on the order of tens to hundreds of threads, this works well. But even with 128 cores, you are limited to 128-way parallelism. Now, with hyperthreading, you might be able to reach 258 threads, but still, this does not scale to thousands of concurrent operations some workloads demand. That is where the GPU becomes relevant. To understand the GPU architecture, specifically as a programmer, it is best to start from the streaming multiprocessor, or SM for short. SM consists of many cores, control unit, and L1 cache, which is shared by the cores. The design of the GPU scales this building block to many units, with the addition of L2 cache to optimize data movement from DRAM. Unlike CPUs, GPUs are built to maximize throughput rather than minimize latency. Instead of a few complex high-performance cores, GPUs use many simpler, low-power ones. This allowed them to handle far more operations at once. The design came from graphics rendering, computing millions of pixel colors in parallel. Each pixel is independent, so what matters isn't how fast one pixel finishes, but how many you can process per second. This approach has led to the modern GPU architecture we see today, with thousands of simple cores instead of a few complex ones. For example, the NVIDIA H100 has over 16,000 cores, making it extremely well suited for AI workloads, which involves massive number of matrix, vector, and matrix-matrix multiplications. To keep these cores busy, the GPU provides extremely high memory bandwidth, on the order of thousands of gigabytes per second. This level of bandwidth is essential to keep thousands of threads across all SMs continuously supplied with data, ensuring the hardware stays fully utilized. Comparing the CPU and GPU architectures side by side, you can see that more of the GPU's silicon area is dedicated to compute cores, while the CPU allocates a large portion to control logic and its multi-level cache system. In other words, the GPU prioritizes compute density, whereas the CPU invests more in sophisticated control and memory management. In summary, the design goals for these two architectures are fundamentally different. CPUs optimize for latency, minimizing time to solution for individual tasks, while GPUs optimize for throughput, maximizing operations per second across all execution units. CPUs have a few powerful cores with complex control logic, while the GPU has thousands of simple cores with simpler control logic. CPUs handle tens to hundreds of threads efficiently, while GPUs require thousands to millions of threads to reach peak performance. CPUs provide 50 to about 500 gigabytes of memory bandwidth, while GPUs provide thousands of gigabytes per second in memory bandwidth. Neither architecture is universally superior to one another. That's why most of the time you see both the CPU and GPU in the same system, and the CPU does what it is best at doing, and whenever there's a massive data parallel operations that need to be done, it can hand that over to the GPU to perform those operations. In the next video, we'll look at the fundamentals for CUDA GPU programming and start with a simple hello world example. Thank you.